A2 Trigonometry Lecture number 3. We'll be further working on identities, but majorly on double angle. Let's say an example question. We have sec 2 theta plus tan 2 theta equivalent to cos theta plus sin theta upon cos theta minus sin theta. Now, since we need to prove the identity here, we need to understand that your sec 2 theta can be written as 1 upon cos 2 theta, whereas tan 2 theta can be written as sin 2 theta upon cos 2 theta. These are your identities. That means sec 2 theta is 1 upon cos 2 theta. Normally, sec theta is 1 upon cos theta. So, if we just write down sec 2 theta can be written as 1 upon cos 2 theta plus tan theta, tan 2 theta can be written as sin 2 theta upon cos 2 theta. Now, considering one thing, that is cos 2 theta is in the denominator. We can take down the LCM, and if we take down the LCM, this can be written as cos 2 theta, and this should be 1 plus sin 2 theta, which means further on, if we want to solve this, we will be working on sin 2 theta. Sin 2 theta is 2 sin theta cos theta. If I just write down this identity, because this is important, sin 2 theta is 2 sin theta cos theta. Similarly, cos 2 theta is written as three different identities: cos theta, cos square theta minus sin square theta. Cos 2 theta can also be written as 1 minus 2 sin square theta, and cos 2 theta can also be written as 2 cos square theta minus 1. So, in this case, what we can do is we have 1 plus 2 sin theta cos theta divided by, now, since I need to understand that what do I need to prove? I need to prove cos theta plus sin theta, right? Since I need to prove cos theta plus sin theta upon cos theta minus sin theta. So out of the three identities that I have, the only identity that looks familiar to what I need to prove is cos square theta minus sin square theta. Considering this, I can just open up using the cos 2 theta that is there. This cos 2 theta can be opened as cos square theta minus sin square theta. So writing it down, cos square theta minus sin square theta. Since I know that cos square theta minus sin square theta is there in the denominator, and this 2 sin cos theta is also there, we can change this 1 to cos square theta plus sin square theta, because sin square theta plus cos square theta is basically 1. So using this method, we can say that in this place of 1, we can write down sin square theta plus cos square theta plus 2 sin theta cos theta upon cos square theta minus sine square theta. Since I need cos square theta and sine square theta in the denominator, and even in the question it says cos theta minus sine theta, I'll make sure that we keep cos square theta initial and then write down 2 sine theta cos theta plus sine square theta, because in this form we can change this to identity. Now, what kind of identity can be changed? This thing can be changed to a plus b square. This thing can be changed to a plus b square, where this can be taken out as a, this can be taken out as b. So this should be cos theta plus sine theta whole square can be changed. And whereas denominator can be changed to a plus b, a square minus b square, which can be a plus b and a minus b. So that means that cos square theta minus sine square theta can be changed to cos plus sine theta and cos minus sine theta. So if we just open this thing up, we need to close our numerator in the form of a plus b. So this will be cos theta plus sine theta whole square upon cos theta minus sine theta and cos theta plus sine theta. Cos theta plus sine theta is cancelled out. Cos theta minus sine theta plus sine theta is cancelled out, plus the square is cancelled out. Because square means two different brackets can be solved together. So the answer for this would be cos theta plus sine theta upon cos theta minus sine theta. Hence, this is proved. Okay, ji. Let's just move to another example. One minus cos 2a plus sine 2a upon 1 plus cos 2a plus sine 2a is equal to 10a. Now, since I need to prove 10a, which means the requirement of such question will be that 10a is basically sine a upon cos a. 10a is sine a upon cos a. So in general, in this numerator, I need to have sine, and in denominator, I need to have cos. Sine 2a can be opened as 2 sine a cos a only. But cos 2a has three identities that we already discussed in the last question. These were the three identities in which cos 2a was cos 2 theta was cos square theta minus sine square theta. Cos 2a was 1 minus 2 sine square theta. And cos 2 theta was also 2 cos square theta minus 1. So in the numerator, we can use this. In the denominator, we can use this so that we can have sine and cos. So moving further with the same question, let's just solve this. We know that 1 minus, we need sine in the numerator. So 1 minus 2 sine squared a plus 2 sine a cos a can be used in the numerator. Whereas in the denominator, 1 plus 2 cos square a minus 1 plus 2 sine a cos a can be used. In this regard, we can say 1 and minus 1 is cancelled, 1 and minus 1 is cancelled, right? But obviously, this negative sign will be used, considering that this should be 2 sine square a plus 2 sine A cos A upon, this should be 2 cos square A plus 2 sine A cos A. Now knowing this, we can take down the common between the numerator and the denominator. We can see that the common between these two is 2 sine A. 2 sine A. So 2 sine A is common. We are left with sine A plus cos A. We are left with sine A plus cos A in the numerator. In the denominator, we can take 2 cos A as common. So this would be cos A plus sine A. So sine A plus cos A or cos A plus sine A are same. These two things are cancelled. 2 and 2 are cancelled. So what are we left with? We are left with sine A upon cos A, which is equivalent to what? 10A. The question told us to prove to get what? 10A. Let's move to the third example for the lecture. Cos 4 theta equivalent to or identical to x8 cos to the power 4 theta minus 8 cos square theta plus 1. If you just see that cos 4 theta is or can be written as cos 2 theta plus 2 theta. And normally cos A plus B is cos A cos B minus sin A sin B. This is a general identity of compound angle identities where this can be used because 4 theta has been shifted to what? 2 theta and 2 theta. So considering the same, what we can do is we can write down cos 2 theta plus cos 2 theta multiplied by cos 2 theta, whereas since it is plus sin 2 theta multiplied by sin 2 theta. Knowing the fact that cos 2 theta can be written as cos 2 theta square minus sin 2 theta square. Since we need to prove that we 8 cos to the power 4 theta minus 8 cos square theta plus 1. Cos 2 theta can be opened as 2 cos square theta minus 1 whole square minus 2 sin theta cos theta whole square. Because sin 2 theta is 2 sin theta cos theta and cos 2 theta is 2 cos square theta minus 1. Why did I do this? Because the identity is in cos. So we need the required answer in cos. So now considering cos square 2 cos square theta minus 1 whole square, we can open this as 4 cos to the power 4 theta minus 4 cos square theta plus 1. We use the identity of A minus B whole square minus 4 sine square theta cos square theta, because this square is on 2, this square is on sine, this square is on cos. Now again we got sine. So sine square theta. Now it's sine square theta, not sine 2 theta. So what we can do is cos 4 theta minus 4 cos square theta plus 1. Now this negative sign is there, 4. This should be sine square theta is 1 minus cos square theta, and cos square theta is multiplying as well, which means 4 cos 4 theta minus 4 cos square theta plus 1 minus 4 cos square theta minus 4 cos square theta, and this should be plus 4 cos to the power 4 theta. Now 4 cos 4 theta plus 4 cos 4 theta is 8 cos 4 theta minus 8 cos square theta plus 1. So this is proved to what was required in the early question, that cos 4 theta can be written as 8 cos to the power 4 theta minus 8 cos square theta plus 1. So here's another example. If you just see that, if you just open sine 2 theta, sine 2 sine theta cos theta. Now at this point, this thing will be blocked and you will not be able to reach to the right hand side. So what we do is we try to open the right hand side towards the left. So this should be 2 tan theta divided by 1 plus tan square theta. Why did we use this sign? Because tan theta can be shifted to 2 sine theta upon cos theta divided by sec square theta, which means 2 sine theta upon cos theta divided by 1 upon cos square theta. Now, since I can reciprocal this, 2 sine theta upon cos theta multiplied by cos square theta. So, cos and square is cancelled. You are left with 2 sine theta cos theta, and 2 sine theta cos theta is sine 2 theta. So, this is proved from right to left. Remember, normally there is this mistake that tan square theta is opened as sine square theta upon cos square theta. So in this way, this tan square theta will be opened as sine square theta upon cos square theta. Then eventually you will end up having lot of working doing, and there might be a possibility you might not even get to the answer. So it's better that 1 plus tan square theta is basically sec square theta, and the sec square theta is basically changed to 1 upon cos square theta, and then eventually you'll get back to the answers. Now again, this is another example that cos 2 theta can be opened as cos square theta minus sine square theta, 2 cos square theta minus 1, 1 minus 2 sine square theta. But the best way is to make sure that we solve the right hand side. So this is 1 minus tan square theta divided by 1 plus tan square theta. Now, obviously 1 plus tan square theta can be changed to sec square theta, but 1 minus tan square theta will be 1 minus sine square theta upon cos square theta divided by sec square theta, and this should be cos square theta minus sine square theta upon cos square theta and divided by 1 upon cos square theta. If I reciprocal this answer cos square theta will go towards numerator. So cos square theta and cos square theta is cancelled out. So what are you left with? Cos square theta minus sine square theta. So this can be closed with cos 2 theta. Hence, this is proved. Okay, here's another example question that we have. Cos 3 theta. So we can write this thing as cos 2 theta plus theta, which can be cos 2 theta cos theta minus sine 2 theta sine theta. Cos 2 theta, since we need the answer in cos, we can always write this thing as 1 minus 2 cos square theta multiplied by cos theta minus 2 sine theta cos theta multiplied by sine theta. So this thing should be cos theta minus 2 cos cube theta minus 2 sine square theta cos theta. So if we just solve 2, this should be 1 minus cos square theta cos theta. So cos theta minus 2 cos cube theta minus 2 cos theta minus cos cube theta. Cos theta minus 2 cos cube theta minus 2 cos theta plus 2 cos cube theta. Further on, now there is one little issue that we did. The cos 2 theta is basically your 2 cos. When we multiply this, we will be opening it as, let's just solve this throughout again so that the error that we have done can be resolved. So let's just, so it will just take a few more minutes just because of the little concept. Considering this will be 2 cos square theta minus 1, and this should be cos theta minus 2 sine theta cos theta multiplied by sine theta. Now we have cos 2 cos cube theta minus cos theta minus 2 sine square theta cos theta. So 2 cos cube theta minus cos theta minus 2 sine square theta will be 1 minus cos square theta cos theta. So this thing can be opened as 2 cos cube theta minus cos theta minus 2 cos theta plus 2 cos cube theta. So what do we have? We have 4 cos cube theta minus 3 cos theta. Hence proved the identity that was required. So this was from the lecture 2. This was from lecture number 2. This was from lecture number 3. So we have almost covered few identity questions through lecture 1, lecture 2, and lecture 3.